Hello physics, welcome to another flipped lecture. We're going to be talking today about chapter 18 and electrical charge. For those of you that hate math, you're going to love this chapter. This is a bunch of concepts and only one math equation, so it is very math light. But those of you who like math, don't worry. We'll get back to you next chapter. Chapter 19 has loads of math. So anyway, we aim to please here at Calvary Chapel Christian School. So we're looking today at chapter 18 from the BJU physics book. We're looking at the introduction of the concept of electricity and electrical charge today. So let's get into it. Electrification is the concept for chapter 18a. And it goes through a lot of the history of how we got to the idea of electricity. And you should read that. You should be familiar with it. But I will not test you on names and dates and old terms to things and things of that nature. So read it, go, oh, look, there you go. There's the history of it. I will not hold you accountable for the history of the idea. We want to look at what the idea is today. So the nutshell of the idea of electrification and electrical charge is that when some material, some substance, has more or less electrons than it used to as a neutral thing, then we say that it is charged. And you're familiar with that idea when it comes to chemistry, because chemistry frequently uses these charges to explain ionic bonding and even partial charges for polarity. So similar idea, same concept. Something has more electrons than it used to, so it's got a negative charge to it, or it has fewer electrons than it used to, so it has a positive charge to it. We've talked about it with regard to chemistry. Now we're going to talk about it with regard to physics. So the charge present on a material, because it has gained or lost electrons, in chemistry, we called it an ionic charge, and here we're calling it an electric charge, or a static electric force. And those forces can attract or repel. And just like we learned in chemistry, and you've already had this concept once in physical science, similar charges repel each other, and opposite charges attract each other, right? And so opposites attract is a phrase you've heard a bunch, and that is rooted in this concept of opposite charges. So that is the law of charges, that unlike charges attract and similar charges repel. We measure electrical charge in a unit called a coulomb. A coulomb. And a coulomb is the charge that is produced by 6.24 times 10 to the 18th electrons. It's actually a very small amount of electrical charge, but it takes a whole lot of electrons to make that much charge. So a coulomb, 6.24 times 10 to the 18th electrons. I'll always, give that number to you if you need to know it, but that will show up in some math later on in chapter 19. Okay, so again, law of charges: opposites attract, like charges repel. If you remember from physical science, we introduced you to the concept of force lines here. So force lines are a way of representing an electric field. Force lines are always drawn from a positive source going to a negative source. And so they are drawn to show what would a hypothetical positive test charge do. It would run away from the positive and go toward the negative. Okay, so when you see these lines, that's going to represent force lines between electrically charged items. And just another way of looking at that, if you had two negatively charged objects and you were to hold them on strings near each other, they will repel. And similarly, if you have two positively charged objects and you hold them next to each other, they will repel. If you have a negative and a positive, they will be attracted to each other. And we'll do things like this in class with pith balls and stuff like that. Electrification. We're continuing with the concept there. So how do you conduct charge? How do you move charge from one material to the other? Something that can take an electric charge, a surplus of electrons, and move it from one place to another. If the electrons can flow across the material, we call that a conductor. Conductors are materials that have mobile electrons. So when electricity moves through a wire, it is not the same electron that enters the wire, travels through the whole wire, comes out, and makes your light bulb go up. Right? Go on, not go up, go on. That's not the same electron. What happens is the electron from the power company jumps onto the wire, and they all kind of leapfrog down the wire, and one is kicked off the end, and that's one of the ones that goes and makes your light turn on. So electrons move and flow along the materials that we would pass electricity down. And those things are called conductors. They have to have loosely held mobile electrons, and almost all the time, a good conductor is a metal. Metals tend to be good conductors of electricity. Okay, materials that do not conduct charge because they don't have free electrons, we call insulators. So an insulator would be something like rubber, where an electron tries to jump onto the rubber and nothing happens. So it doesn't have free electrons that it can pass down the line and have something jump off the other end and so conduct the charge. And then there are some materials that are insulators, except in unique circumstances when they can be tricked or fooled into conducting electricity. And those materials we call semiconductors because they're not normally conductors, but they can be made to be conductors. And semiconductors, their discovery led to the technological revolution. Computers, radios, almost all electronics are based on semiconductors, materials that are insulators, but then we do something to them and then they let electricity go through. So it becomes a switch of sorts. And that is the foundation for most technology that you're running into today. Okay, let me show you some pictures of that. So again, a conductor, electrons can flow through easily. So think of like a highway for electrons, okay? A semiconductor, silicon, your computer chips here are made out of semiconductors. And semiconductors are usually closed, but they can be tricked into letting electrons flow through. Now the picture I found has a narrow street, but basically it should have been a gate with somebody standing at the gate and only once in a while letting electrons through. Okay, it's kind of not the best picture. An insulator, like the rubber on this wire, keeps electricity from flowing. It stops the flow of electricity. It does not let electrons go through. So kind of like this road that is still under construction across the river, you're not going to be able to drive down there. Okay, it stops the flow. So a wire that you would be used to seeing has conductors in the middle and insulators around the side to keep the signal entrapped in the wire. Alrighty, detecting charge. How do I know if there is electrical charge there? In the old days, and again, your book spends a lot of time on history in this chapter. In the old days, the best they could do would be something like this, where you have two pieces of foil and they are attached to a rod, and there's a steel ball at the top, and if you put something on the steel ball that has charge, then the electrons flow down here and distribute themselves evenly throughout all of the metal here. And then these two leaves of foil will separate because they have like charge. And then you go, oh, look, that thing that I touched to this had a charge. And you can still use things like this. You can still buy electroscopes that look like this, or you can make them in the lab. But it's kind of old tech. We now have spiffy things that look like ray guns that are able to detect electric fields, and if you bring them close to charged objects, they'll say, yes, that has a charge. There are also smaller handheld versions that are made today that are about the size of a magic marker, and they are able to detect electric charge too and give you digital readouts for the strength of the field. So we have a variety of digital tools today that we can use, but this is kind of the old concept, and the concept still works. If you put electrons here, these things will separate, and then you'll go, yep, that had a charge. So that is how you would detect charge then and now. How do you conduct charge? How do you get something to have a charge in the first place? You can do that a couple of different ways. You can usually rub something and strip off electrons and so give it a charge, or touch something that is charged to this other object and now it has a charge too. And so by contact you can charge an object. Or you can do what's called induction, where you bring a charged object near some other object and the electrons on the second object arrange themselves because of the presence of the charge on the first object. So let's pretend that my coffee cup was charged, and I had an excess of electrons on my coffee cup, and my water bottle was neutral. But as I brought my coffee cup near the water bottle, the electrons on the water bottle would respond to the presence of a charge here and would run away. And they would pile up on the other side of the bottle so that the near side of the bottle to the excess of electric energy would wind up being slightly positive, and this region of the bottle would wind up being slightly negative. Now, if I were to have that situation and then touch it with my body, which will ground it out, on the far side, all of the electrons that were piling up over here would run down my body to the ground, and then I could again hold it only by the plastic cup, and now electrons have left this, and this whole bottle would then be positively charged. So you can get a charge by contact. You can get a charge by holding something nearby, which is called induction. And if you can ground the second object that you're bringing an induced charge to, that charge will be permanent. It'll stay there, okay, until you allow it to leave and do something else. So that brings us to the concept of an electrical ground. When I touched the bottle in the pretend analogy there, the electrons would have run down my body into the ground. What do we mean by grounding? Well, the Earth is really, really big, and the Earth has lots and lots and lots of electrons. And if I add a few more electrons to the Earth by, having a circuit send its electricity down into the ground, the Earth doesn't respond. The Earth is too big to care. It doesn't notice the additional amounts of electrons. So the charge of the Earth doesn't change. And so we use the word ground to mean an electron sink. It can absorb huge amounts of electrons, or it can give up huge amounts of electrons. And it itself really doesn't give a rip. Its electrical charge doesn't change. So no meaningful change in its charge. The Earth was the first object that we thought of when we were thinking of what could be an electrical sink. And so the concept was called a ground. But now other objects can serve as ground as well. Okay? So that's the idea there. Don't you love it? We have almost no math. Isn't this fun? So charging a neutral object, and now we have mosquitoes though. That's forever captured. It's really, really fun. Charging a neutral object by conduction, I talked about. You could bring a charged object to something and touch it, and once it touches, the electrons flow onto it, and then it is charged. So my electroscope would show a charge. Similarly, by induction, if you have a charged object and you bring it near something, the electrons are going to want to run away and go over here. And then you separate the two, and now the excess electrons are here, and this one winds up with a deficit, so it's positively and negatively charged. That's induction. You can do the same thing with the ground, as I talked about. Bring a charged object near something else. The electrons try to run away. You touch it with a ground, and they go, oh, thank you, I'm going to leave now. And now you wind up with a positive amount, charge left over on the object. Okay, charging by contact or charging by induction. Electrostatic forces. This is the one math equation that we have this chapter. So we can talk about the strength of a magnetic field between two objects, and the math that you use looks almost exactly like the math for gravity. The equation is in the same format, and if you remember how gravity works, gravity was the mass of one object, the mass of another object, divided by the square of the radius of their separation times the gravitational constant. This looks exactly the same, only it's the charge of one object times the charge of another object, divided by the square of the radius of their separation, how far apart they are, right? And then it's not times the gravitational constant, but times Coulomb's constant. And if you do this math, you will calculate the force between two objects. Now, are they attracting with that amount of force or repelling by that amount of force? Depends on their signs. Are they positive and negative, or positive and positive, or negative and negative? And we already talked about the laws of forces, the laws of charges earlier in this lecture. Okay, so the only number that you have to remember here, and you don't even have to remember it, I'll always provide it for you, was Coulomb's constant, 8.99 times 10 to the 9th. If you just remember, it's a lot like 9. 8.99 is really close to 9 times 10 to the 9th. That will help you remember that number. And that is the constant that allows this math to come out to the right answer. So you put in charges in coulombs and the radius in meters, and then you will get force in newtons. Okay, so that's the only math that we have this chapter. Let me show you an example problem. These two balloons are both negatively charged. with charges of negative 1.5 times 10 to the negative 5th coulombs. So a very small electrical charge. They are separated by a distance of 7 centimeters. What is the repulsive force between them? So how much are they pushing against each other to stay away? Notice that gravity is not strong enough to make them come together and touch. The electrostatic forces are keeping them separate. So here's our equation. Q1 and Q2 are the charges of the two objects. They're both the same in this instance, so 1.5 times 10 to the negative 5th and 1.5 times 10 to the negative 5th. Here's Coulomb's constant, 8.99 times 10 to the 9th. And then they're separated by 7 centimeters, so we're going to turn that into meters. And we multiply this together and we get this number. Divide by the square of their radius of separation, and we get this number. This times Coulomb's constant gives us this number, and we need to correct for significant digits, and we have 410 newtons. And that's the force that's pushing those two balloons apart. Okay? That's it, folks. It doesn't get any harder than that for Chapter 18. Let me know if you have any questions. You can put them in the comments field below, or I'll see you tomorrow in class. God bless you. Have a wonderful evening.